Okay, so let's take a look at that shortcut. Remember when we did this question a little while ago that we got an answer with no remainder? Well, there are times when, whether or not you have a remainder, you can actually take the divisors and not have to do long division. We actually do a different kind of division called synthetic division, which is a shortcut. However, synthetic division only works if you have a binomial divisor. So you need to have something like x minus 1 and not something like x squared minus x plus 1. So here's how it works. First of all, write down the root. So you solve that the polynomial divisor for equal to 0 and you write down the root. Then write down next to it all of the coefficients of your polynomial function. And again, you need to create a column for each degree of x. So that's a little typo, that's 3x cubed. So you have a 3, that's x cubes, 2 x squareds, x's, and constant terms. Then you draw a line, leave a one-line space, and then you draw a line underneath. And here's the shortcut, and it's a little easier to explain through than to write the steps down. But you add this way, and you are going to end up doing some multiplication to get the next numbers. So it looks like this. 3 plus 0 is 3. 1 times 3 is 3. 2 plus 3 is 5. 1 times 5 is 5. Negative 3 plus 5 is 2. 1 times 2 is 2. And add gives me 0. Now, how do these coefficients compare to the numbers down here? Well, there they are. They're exactly the same. And this was our remainder of 0. And it works this way every single time. So how do I translate this up to this one? Well, this is now my constants. This is my x to the power of 1, and this is my x to the power of 2. So just count up. Let's take a look at another example of this, and it is so much faster. Okay, so x plus 1 is my divisor, but I put the root in here, which is minus 1. Then I start labeling coefficients. So 2, that's degree 4, degree 3. There's no degree 2 term. There's 0x squareds, but there's a degree 1 and a constant term. I write my line. I actually put another line down like this so that I separate my remainder. It's all by itself, and then I start working. 2 plus 0 is 2. You always just add the first one and multiply. Add. Oh, I can't even add today. Add and multiply. Add and multiply. Add and multiply. Done. So the answer to this is, well, there's a remainder of negative 4. So when I do this division, I'm going to end up with negative 4 and the original divisor. So that's the r over d of x part. And my quotient is, well, there's a constant term of 3. And before that, there's negative x. And before that, there's x squared. And before that, there's 2x cubed. So I end up with 2x cubed plus x squared, take away an x plus 3, plus the remainder over the divisor. This is much, much faster, as I've said a couple times. Let's take a look at two more examples. X to the 7th minus 3x to the 4th minus 2x squared minus 72 is going to get divided by x minus 2. So there's my root, and now I start listing my coefficients. 7 term, 6 term, 5 term, 4, 3, 2, 1, and constant term. This is going to look like a lot, but it's still a lot faster than synthetic. Long division. Add, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add, 18, multiply, 36, add, multiply, add. Oh, beautiful. Remainder is 0. So that means when I do this division, I end up with this polynomial function. Now, constant term, degree 1, degree 2, degree 3, degree 4, degree 5, degree 6. So it's 1x to the 6th, 2x to the 5th, 4x to the 4th, 5x cubed, 10x squared, 18x's, and 36. And one last example for us. Example, 4x cubed plus 2x squared minus 8x minus 10 gets divided by, and we've got a binomial divisor. But there's one other condition about the binomial divisor for synthetic division to work. And that's the fact that for it to work, the binomial divisor has to have a coefficient of 1. And this one doesn't have a coefficient of 1, it's a coefficient of 2. But if I do a little bit of factoring, I do actually end up with a coefficient of 1 for the factored part. And whenever you take something and you divide, you can divide by both bits, which means I can divide this by 2 and I can divide it by x minus 1/2. So if you split it up this way, then you get this kind of a question. Well, 1/2 is my root, and I'll put the coefficients down, 4, 2, minus 8, minus 10, and add, multiply, add, multiply, add, multiply, add. And so what I've done now is taken my original question, I've divided by 2x minus 1, but I've only divided by the x minus 1/2 of 2x minus 1. So it looks a little bit like this. When I take that polynomial function and divide it just by the x minus 1/2, I get 4x squared plus 4x minus 6 plus negative 13 over x minus 1/2. But I need to divide it by 2x minus 1, or 2 x minus 1's. So if I multiply this denominator by a 2, that means I'm really dividing this whole thing by another factor of 2, which means I have to divide this by another factor of 2 and divide this by another factor of 2. And so I can do that. This will be what I want to solve, but now I have to divide all these. So it's really 2x squared plus 2x minus 3, and not equals, just minus, and this can be 13 over 2x minus 1/2. So it is possible to get a solution to the question. Again, this is the original question that was asked. It is possible to get a solution to that original question. You just have to do a little manipulation so that you get the leading coefficient to become a 1. This is a pretty high-level question, and you probably shouldn't expect to see too many of these. Okay, we're all done for today.